Hello everyone. So in this hour we are going to talk about electrostatics and gravitation. This is the beginning of a new series. Here we will talk about entire electrodynamics, but about the first chapter of electrodynamics, which is the electrostatic, I am taking it in parallel with gravitation. Why? Because the formula looks the same. There is only one difference between gravitation and electrostatic that has to be taken into mind. When you are playing with gravitation, you are playing with masses, and masses always attract. When you are playing with charges, then charges can repel as well as attract. And if you keep this simple thing in mind, understanding gravitation and electrostatic in parallel becomes really easy. So without wasting time, let's start learning gravitation and electrostatic. So why I'm teaching you both of them simultaneously at the very first place? Because the forces looks the same. So now we will start talking about charges. So if you have got two charges q1, q2 separated at distance r, the force is given by k q1, q2 upon r square. Here k is a proportionality constant called the Coulomb's constant. The value of Coulomb's constant for vacuum is given by 9 into 10 raised to the power of 9. Now you can write the unit thinking that k equals to F into r square by q1, q2. Yes sir. The unit of force is Newton. The unit of length square is meter square. The unit of charge square is Coulomb square. So you get the value of K for vacuum to be 9 into 10 to the power of 9 Newton meter square per Coulomb square. But the big question is, why are you saying that this is the value of K for vacuum? For vacuum, the value of K is 9 into 10 to the power of 9. Sir, why are you even using the word vacuum? Because for different mediums, this proportionality constant K has got different value. So, sir, are you trying to say that the force in vacuum is different from the force inside a medium? Yes, that's what I'm trying to say. In vacuum, the force constant is 9 into 10 to the power of 9, but for medium, we take up different values. Now, what we need to emphasize on is different from gravitation here. Gravitational force is always attractive in nature. Gravitational force is independent of the medium present between the two masses, but that's not the case for electrostatic. The force is attractive or repulsive depending upon the nature of charges. If the charges are like charges, then the force is repulsive. So if both the charges are positive or if both the charges are negative, then the forces are repulsive in nature. They try to push each other away. But if the two charges have got opposite sign, one of them is positive, another one is negative, then the two charges try to attract each other. They try to move closer to each other, just like masses. So force is attractive or repulsive depending upon the nature of charges. For like charges, the force is repulsive. For unlike charges, the force is attractive in nature. Now, there is one more way to write whether the charges are like in nature or unlike in nature. If we look at a quantity called the multiplication of charges, let's say q1 into q2. For like charges, q1, q2 will be greater than 0. The multiplication of the charges will be greater than 0. Why? Sir, if you are saying that q1 and q2 are like charges, yes, then either both of them will be positive or both of them will be negative. If both of them are positive, then their multiplication will be positive. If both of them are negative, still their multiplication will be positive. So you can say for like charges, q1 into q2 is greater than 0. And for unlike charges, q1 into q2 has to be less than 0. Why? Because, sir, for unlike charges, if first one is positive, second one is negative, multiplication is negative. If first one is negative, second one is positive, multiplication is negative. So for unlike charges, the multiplication is less than 0. And for like charges, the multiplication is greater than 0. So if q1 into q2 is greater than 0, it means that both the charges are like in nature. Either both of them are positive or both of them are negative. In either case, the force has to be repulsive in nature between the charges. Or if we get q1 into q2 less than 0, it means that one of them has to be positive while another one has to be negative. One of them has to be positive while another one has to be negative. Then the force between the charges has to be attractive in nature. Now the important line, the net force on charge depends upon the medium. The net force acting on one of the charge depends upon the medium. So if you have got them placed inside a medium, then the force is not 9 into 10 raised to the power of 9 q1 q2 upon r square. Then, sir, what to do? We will talk about this in detail once I start talking about Coulomb's law in detail. But right now, let's focus on gravitational law and understand it better in detail. So, how to write gravitational force between two masses in the vector form? If you have got two masses m1 and m2, this vector represents the position vector of mass 2 with respect to mass 1. position vector of 2 with respect to 1. If you have got point A, if you have got point B in space, this vector represents the position of B with respect to A, and this vector represents the position vector of A with respect to B, right? So here, this vector represents the position of mass 2 with respect to mass 1. R21 is what? Position of mass 2 with respect to mass 1, which will be nothing but position vector of 2 minus position vector of 1. That's the meaning of R21. Now tell me, the force applied by mass 1 on mass 2 will be in which direction? Sir, you are talking about gravitation. So, gravitational forces are always attractive in nature. So, the force applied by M1 or M2 will be towards M1. Okay. Now tell me, this force vector is parallel to the position vector of 2 with respect to 1 or anti-parallel to the position vector of 2 with respect to 1? So, sir, the force vector is anti-parallel to the position vector of 2 with respect to 1. The position vector of 2 with respect to 1 is from 1 to 2. And the force applied by 1 on 2 is towards 1, attractive in nature. So, let's make some terminology clear here. The magnitude of this force applied by mass 1 on mass 2 will be equals to universal gravitational constant G into the mass 1 into the mass 2 upon the magnitude of separation between them whole square. So that will be G m1 m2 upon magnitude of separation between them. Magnitude of position vector of 2 with respect to 1 whole square. This will be the magnitude of force. It will look ugly. Do not worry. It's a simple thing. Just stay focused. So this gives us the magnitude. Yes, sir. If I ask you, how will you write a vector of magnitude 5? A vector of magnitude 5 parallel to vector I cap plus j cap. How will you write? So you will say, sir, I have to write a vector of magnitude 5 in the direction of I cap plus j cap. Yes, a vector of magnitude 5 in direction of I cap plus j cap. How to write? See better. You will say the vector I cap plus j cap is a vector of magnitude under root of 1 square plus 1 square, that is under root of 2. I don't want a vector of magnitude root 2. I want a vector of magnitude 5. So what do? If we need to write a vector of magnitude 5 in direction of vector I cap plus j cap, we write a unit vector in direction of vector I cap plus j cap. And this is the whole purpose of defining the unit vector. A unit vector is a vector of magnitude 1. So a vector of magnitude 1 in direction of I cap plus j cap will be given by I cap plus j cap upon its own magnitude, that is root 2. So you will say I cap plus j cap by root 2 represent a vector of magnitude 1 in direction of I cap plus j cap. We need a vector of magnitude 5. So what to do? So this is a vector of magnitude 1 in direction of I cap plus j cap. We need a vector of magnitude 5, multiply with 5. Similarly, if I ask you, write a vector of magnitude 10 in direction of vector I cap minus j cap plus 2k cap. So you will say, sir, if I need to write a vector of magnitude 10 in direction of I cap minus j cap plus 2k cap, how to write? I will write I cap minus j cap plus 2k cap and divide it with its own magnitude. The magnitude of ai cap plus bj cap plus ck cap is given by under root of a square plus b square plus c square. So the magnitude of I cap minus j cap plus 2k cap will be given by under root of 1 square plus minus 1 square, that becomes 1 square plus 2 square. So this gives you I cap minus j cap plus 2k cap divided by 1 plus 1, 2, 2 plus 4, that becomes root 6. Now I cap minus j cap plus 2k cap by root 6 represent a vector of magnitude 1. It's a unit vector in direction of I cap minus j cap plus 2k cap. What is the mission? The mission is to write a vector of magnitude 10 in direction of I cap minus j cap plus 2k cap. This is a vector of magnitude 1. You need a vector of magnitude 10. What to do? Multiply it with 10. So when we multiply it with 10, we get 10 times I cap minus j cap plus 2k cap divided by root 6. So similarly, right now the mission is we need to write a vector of magnitude gm1 m2 upon magnitude of separation between them whole square in the direction of a vector from 2 to 1. But let's get our terminology clear before we use this unit vector method. So we will say F21. What is R21, bachcho? Sir, R21 is position of 2 with respect to 1. So what is F21? Sir, F21 is the force on mass 2 due to mass 1. What is F21? The force on mass 2 due to mass 1. F21 is force on mass 2 due to mass 1. Just like R21 is position of 2 with respect to 1. Now, the force on mass 2 due to mass 1 will be towards mass 1. The direction of force is anti-parallel to the position of 2 with respect to 1. The direction of force applied by mass 1 on mass 2 is anti-parallel to the position vector of 2 with respect to 1. Now you will write the force in vector form as the force on 2 due to 1 equals to the magnitude of force multiplied by negative of unit vector in the direction of 2 to 1. Sir, I am not getting it. Keep calm. Listen here carefully. What is this? Sir, this is R21 cap. What does the cap represent? A unit vector. In which direction? Sir, R21 is the position of 2 with respect to 1. A unit vector here represents a vector of magnitude 1 in the direction of R21, right? But we know that the force will be towards 1. So that's why we have flipped the vector. We have flipped the unit vector, and to flip the unit vector, we have multiplied with minus 1. So we know that the force will have magnitude equals to gm1 m2 upon magnitude of r21 whole square. This will be the magnitude multiplied by direction, that will be a unit vector in direction of r21 with a minus sign. Flip the vector. So here place a square. So what you get is the force on 2 due to 1 is given by gm1 m2 upon r21 whole square into minus times the position of 2 with respect to 1 upon magnitude of position of 2 with respect to 1. R21 upon magnitude of R21 gives you a unit vector in direction of R21. And why the minus sign? Because the force has to be opposite to, the opposite to position vector. Now you can rewrite this as F21. The force on 2 due to 1 in the vector form equals to gm1 m2 into position vector of 2 with respect to 1 upon magnitude of position vector of 2 with respect to 1 whole cube, whole square here and 1 here, so that becomes whole cube with a minus sign. And you can keep this particular formula in mind. Sir, while solving question, do you use this formula in general? No. Then how do you write the force in vector form? Let me teach you. Let's see an example where I won't use the formula per se, but I will use the concept learned in the formula to write the force in vector form. Two masses A and B of 2 kg and 4 kg. So A has got mass of 2 kg, B has got mass of 4 kg, are placed at 2, 3 and minus 1, minus 1. Determine the force by 2 kg on 4 kg in vector form. Determine the force by 2 kg on 4 kg in vector form. So you know the position of 2 kg, 2, 3, position of 4 kg, minus 1, minus 1. You need to write the force by 2 kg on 4 kg in vector form. So visualize the two masses in space. So there is a mass of 2 kg placed at 2, 3. There is a mass of 4 kg placed at minus 1, minus 1. This vector represents the position of 4 kg mass with respect to 2 kg mass. What is the mission? The mission is to find the force on 4 kg mass because of 2 kg mass. Okay, if we need to write the force on 4 kg mass due to 2 kg mass, that will be towards 2 kg mass. What will be the magnitude of this force? So you will say, sir, the position of 4 with respect to 2 will be equals to position of 4 minus position of 2. Position of 4 kg mass is minus I cap minus j cap. Position of 2 kg mass is 2 I cap plus 3 j cap. So this whole subtraction gives you position of 4 kg mass with respect to 2 kg mass. Now minus I cap minus 2 I cap gives you minus 3 I cap. Minus j cap minus 3 j cap, this minus sign, minus 3 j cap gives you minus 4 j cap. So you get the position vector of 4 kg mass with respect to 2 kg mass to be minus 3 I cap minus 4 j cap. Now see, they have purposefully taken such a value 3 and 4. Why? Because when you find the magnitude using under root of a square plus b square plus c square, you get the magnitude to be 5. So the position vector of 4 with respect to 2 comes out to be minus 3 I cap minus 4 j cap. The magnitude of position of 4 with respect to 2, the separation comes out to be under root of minus 3 square minus 4 square, that comes out to be 5. Now you can find out the magnitude of force. The magnitude of force will be nothing but g m1 m2 upon r square. The first mass 2 kg, the second mass 4 kg upon separation between them 5 whole square. This comes out to be the force. They are asking me the force in vector form. So I know the magnitude of force here. I know that the force applied by 2 kg on 4 kg will be attractive in nature. So that force will be towards 2 kg. Yes. And I know how to write a vector from 2 to 4. From 2 to 4. I have written it already. So I can even write a vector from 4 to 2. the vector from 4 to 2 will be flip of it. So that will be 3i cap plus 4j cap. So I know the magnitude of force that I need to write. I know the direction in which I need to write. So now write. So you will say the magnitude of force is 8g by 25. The force will be along the vector, position vector of 2 with respect to 4. Okay. As the force is attractive in nature. So the force will be along the vector, position vector of 2 with respect to 4. We know what is the position vector of 4 with respect to 2. And we have learned that the position vector of 4 with respect to 2 has to be opposite to the position vector of 2 with respect to 4 minus times. So we can say the force in vector form will be the magnitude of force 8g by 25 multiplied by a unit vector in the direction of the vector from 4 to 2. Right? Here you can see I haven't placed the minus sign. If I write here, I can write the same thing as 8g by 25 multiplied by minus times a unit vector from 2 to 4. But I have written from 4 to 2 directly without using the minus sign. Personally, I do not like negativity in my life, so I write it without the minus sign. Now, bachon, you can write unit vector along the position vector of 2 with respect to 4. So you will say, I know the vector, that will be the flip of it, 3i cap plus 4j cap, and divide it with its own magnitude. So you will write this as 8g by 25, the magnitude, multiplied by the position vector of 2 with respect to 4 will be 3i cap plus 4j cap. And the unit vector will be 3i cap plus 4j cap divided by its magnitude, which is 5. So here you get 8g by 25 into 5. In the denominator, you get 125. So you get 8g into 3i cap plus 4j cap by 125. So this is how I personally use the Newton's law in vector form. Personally, I do not use the formula. I just remember that F21 represents the force on 2 due to 1. And I remember that the force is attractive in nature, and I know how to play with the basic vectors. So let's move on to understanding more question on Newton's law of gravitation. Three equal masses M are placed at three corners of an equilateral triangle of side length A. Determine the force on one mass due to the other two. So visualize that you have got three masses, okay, M, 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 placed at three corners of an equilateral triangle, and the equilateral triangle has got side length A. Your mission is to determine the net gravitation force on any one of the mass due to the other two. So you will say on any one mass there will be attractive force due to the other two mass. If we look at the forces on the mass A, now this mass B will attract it towards it with a force g m square upon a square, and this mass C will also attract it towards itself with the force g m square upon a square. So if you visualize the forces acting on the mass A, there will be two forces. This force because of the mass B, this force because of the mass C, and there will be an angle between these two forces. That angle will be of 60 degrees. Tell me kids, force is a scalar quantity or vector quantity? The force is a vector quantity. So when you add up two forces, which type of addition you should do? Scalar addition or vector addition? So always vector addition. That's why do not do this error that the net force on mass A is 2g m square upon a square. These forces are not in same direction. They can't be added up like scalars. Then so what to do? Better use the method you learned to find the resultant of two vectors. If you have got two vectors A and B inclined at some angle theta, then their resultant is given by under root of a square plus b square plus 2ab cos theta. And you have even learned that if you have got two equal forces F, same magnitude F, inclined at angle theta, then the resultant force comes out to be equals to 2F cos theta by 2. I have told you this as this is really important while teaching you vectors. So the resultant force will be 2F cos theta by 2. Here you have got two forces of same magnitude, gm square by a square, gm square by a square, acting at angle of 60 degree. So the resultant force will be equals to 2 into gm square upon a square into cos 60 by 2. What is cos 60 by 2? Cos 60 by 2 is cos 30. And cos 30 is nothing but root 3 by 2. So you get the resultant force to be 2 into gm square upon a square into root 3 by 2. Beta cancel out 2 and 2. What you get is root 3 gm square upon a square. This is a simple question. Now I will use this many a time, so remember this. If you have got two vectors of magnitude r and r inclined at angle theta, any vector, but they should have same magnitude r and r, then the resultant come out to be exactly midway between them, and that resultant has magnitude 2r cos theta by 2. So let's practice more. Based on this question, I am taking up the next example. So the question goes like, if three equal masses m are placed at three corners of an equilateral triangle of side length a, determine the speed with which they must be moving in a circle so as to maintain the triangular formation. What is the meaning of this question? We have just learned that we have got three masses, yes sir. These three masses are placed on the three sides of an equilateral triangle, yes sir. Each mass, let's call A, is being pulled by the other two. So there is a net force on each mass, and that force came out to be root 3 g m square upon a square. Okay, so if these three masses are kept and released, then each mass will start moving towards the center of the triangle, and over the period of time they will collapse at the center. Now what does this question says? The question says if three equal masses are placed at the three corners of a triangle of side length A, determine the speed with which they must be moving in a circle so as to maintain the triangular formation. So these three masses should be moving in a circle so that the net force acting towards the center becomes equals to centripetal force and they maintain the triangular formation. So visualize the three masses and visualize that they are moving in a circle. Now tell me what will be the relationship between the radius of the circle and the side length of this triangle. So you will say, if we think of the radius of the circle and side length of this triangle, first of all tell me kids what will be this angle. So this angle has to be 30 degree. As the whole angle will be 60 degree, half of that angle has to be 30 degree. Now visualize this thing. This half length will be a by 2. So if I just focus on this right angle triangle with length of hypotenuse as radius, the base length as a by 2, and this angle means 30 degree. I can say that r cos 30 will be equals to a by 2. Once I know that r cos 30 is a by 2 and cos 30 is root 3 by 2, so we can write r into root 3 by 2 equals to a by 2, cancel out 2 and 2, your r comes out to be a by root 3. Once you know the relationship between the radius of the circle and the side length of this equilateral triangle, most of the part of the game is over. Why? Because we have learned that for a particle to move in circle, the net force acting towards the center should be equal to centripetal force. Here we already know what is the net force acting on each mass. If we visualize the force acting on mass A, we got that the force acting on mass A came out to be root 3 g m square upon a square. And this force has to be equals to the centripetal force. So if this mass A moves at this instant with a speed v, then this force acting towards the center, root 3 g m square upon a square, has to be equals to mv square by r, where r will be equals to a by root 3. Game over. So you will say, if each mass moves in a circle, the net force acting towards the center has to be equals to centripetal force. The net force acting towards the center is root 3 g m square upon a square. This has to be equals to mv square upon r, and in place of radius you can substitute a by root 3. Once you do this, this root 3 moves from denominator of denominator to the numerator, and these two root 3 on both the side get cancelled, and 1a get cancelled with 1a, so you get v to be equals to under root of gm by a. V comes out to be under root of gm by a. What is a? A is the side length of the triangle, not at all the radius of circle. How to determine the relationship between the radius of circle and the side length of triangle? You will say, so just drop a perpendicular here. This angle is 30 degree and you can use r cos 30 equals to a by 2. So easy. Okay. So let's move on. Now the question, if four equal masses m are placed at four corners of a square of side length a, find the net force on one of the mass. So last time we took three masses. This time we are taking four masses. So visualize the four masses m, 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 m. I'm drawing them big, but you must think of point size masses. Now here, on one of the mass, visualize the force due to all the other three masses. So on this mass A, because of the mass B, there will be an attractive force, and this attractive force will be towards B, and this force will have magnitude gm square upon a square. On this mass A, there will be also force because of D towards itself, and that force will be gm square upon a square. And on this mass M, there will be also force because of C. But the force because of C can't be written as gm square upon a square because the separation between the masses is not A. The separation between mass A and C is same as the length of the diagonal of the square, which is root 2a. So force by C on A will also be attractive in nature towards C, and that force will be equals to gm square upon root 2a square. Now what we need to do is we need to find the net force on mass A, and to find the net force on mass A we need to find the resultant of these three forces. To our advantage, the resultant of these two forces gm square upon a square and gm square upon a square comes out to be in the same direction as the force by the C. So first visualize the force by the C. That can also be written as gm square upon root 2a whole square, that becomes 2a square. So this is the force by the C. Now when you add up these two forces acting at angle of 90 degree, their resultant come out to be root 2 gm square upon a square. So the net force on mass A comes out to be gm square upon 2a square plus root 2 gm square upon a square. So the net force comes out to be, take gm square upon a square common, half plus root 2. This is the net force on any one of the mass. They might ask you the same type of question. If these four masses also move in a circle maintaining the shape, then what is the speed? So you can do the same thing. You can write the net force acting towards the center, gm square upon a square into half plus root 2 equals to mv square by r. And this time you will take the radius as half of the length of the diagonal, and the half of the length of the diagonal will be equals to root 2a by 2. So if all the masses perform circular motion like in the previous question, then you can write the net force acting towards the center has to be equals to the net centripetal force, that will be mv square upon r, and the radius of this circle will be nothing but half the length of diagonal, that will be root 2a by 2, that becomes a by root 2. So if you substitute r here and f net here, you can find the speed if asked in the paper, but you should know how to find the f net. So now let's move on to the next heading, and now we will talk about null point. So what is null point? Null point, the point at which if a mass is placed, it experiences no force. When I talk about null point in electrostatics, the definition is the same. The point at which if a charge is placed, it experiences no force. So what is null point? For gravitation, the point at which if a mass is placed, it experiences no force. And for electrostatics, the point at which if a charge is placed, it experiences no force. So a point on which if a mass is placed, it experiences no force when we are talking about gravitation. Now visualize that you have got two masses m1 and m2 separated by distance d. Where can you place a third mass so that it experiences no force? If I place the third mass here, gravitation force is always attractive in nature. So the first mass will attract it towards itself. The second mass will attract it towards itself. Hence, the sum of these two forces can't be zero as they are in same direction. So this place can't be the position of null point. If I place the mass here, the first mass will attract it towards itself. The second mass will attract it towards itself. And again, the net force can't be zero because these two forces are in same direction. If I place the mass somewhere else in space at a random position, let's say here. If the mass is placed here, the first mass will attract it. The second mass will attract it. And again, these two vectors acting at some angle can't have a zero resultant, right? Their resultant will be somewhere here. They can't cancel out. For two vectors to cancel out each other, both should have same magnitude and they should act in opposite direction. Only then two vectors can cancel out each other. So where can you find the null point? So the null point must be present somewhere between the masses and closer to the mass of smaller magnitude. Why I am saying this? Focus. Now, if you place the mass between them, the first mass will attract it, the second mass will attract it, and now these two forces can cancel out. But this mass should be placed closer to the mass of smaller magnitude. So if m1 is less than m2, then m should be placed closer to m1. If m2 is less than m1, m2 is smaller, then this mass m should be placed closer to m2. Why? We will get it from the formula. So we can say that the mass should be placed on the line joining to the masses in between them. The third mass, to find the null point, should be placed on the line joining the masses and in between them. Not outside here, not outside there, not somewhere else in space. The third mass should be placed on the line joining the masses and somewhere in between them. So let's say you place the third mass at a distance x from the first mass. If you place the third mass at a distance x from the first mass, the force applied by first mass on this mass m will be gm1m upon x square. Now the distance of this mass from the second mass will be d minus x. So the force applied by second mass will be gm2m upon d minus x whole square. Now bachcho, you can cancel out gm and take under root both the side. When you take under root both the side, on the left hand side you get root m1 by x equals to root m2 upon d minus x. Now once you have established this, root m1 by x equals to root m2 upon d minus x, on cross multiplying you can find out the value of x. How? Here you will say take this whole term to the left hand side, so you get root m1d minus root m1x equals to, take this x on the right hand side, root m2x. Now bring this whole root m1x to the right hand side, you get root m1d equals to root m1 plus root m2 into x. So x comes out to be nothing but root m1d upon root m1 plus root m2. So x comes out to be root m1d upon root m1 plus root m2. Similarly, the distance of the null point, what is null point? Where a third mass should be placed so that it experiences no force from the mass m2 comes out to be root m2d upon root m1 plus root m2. Okay. You need to keep this formula in mind. Now bachcho, here one important thing. Notice that the distance of the null point is independent of the mass to be placed at the null point. Why? Because here the term m and m got cancelled. So if even you place a mass m, or you place a mass 4m, or you place a mass 6m at the null point, once you know that the null point for mass m1 and m2 is at a distance root m1d upon root m1 plus root m2 from the mass m1, no matter what the mass you place there, it will experience no force at all. Now let's practice a question based on null point. The question goes like, if the mass of earth is 81 times the mass of moon, mass of earth is 81 times the mass of moon, and the distance between them is d, at what distance from earth a mass should have no net force acting on it? So visualize the separation between earth and moon to be d. The mass of earth to be 81 times the mass of moon. So we have taken the mass of moon as m and the mass of earth as 81m. At what distance from the earth, if you place a mass, let's say a mass m dash, then it will experience no force at all. It will experience no force at all because the force of attraction due to earth will cancel out the force of attraction due to moon. Now I have said already, the null point, the point at which the mass will experience no force, will lie closer to the smaller mass. That's why I have placed this mass to be closer to the moon. So we get from here, assume a mass m dash to be placed at distance x from earth. If we place a mass m dash at distance x from earth, so the force by earth will be g into 81m, the mass of earth, into the mass m dash placed upon x square, and this has to be equal to the force by the moon, so that the net force becomes 0. So the force by the moon equals to g into mass of moon into m dash upon d minus x whole square. Now bachcho, quickly cancel out g, m dash, m dash. So on the left hand side you get 81 by x square equals to 1 upon d minus x square. Taking under root both the side, you will get 9 by x equals to 1 upon d minus x. Now cross multiplying, you will write 9d minus 9x equals to x. 9d equals to 10x. X comes out to be 9d by 10. So on solving, you get x equals to 9d by 10. It means that the null point is at a distance 9d by 10 from earth, 9d by 10, and at a distance d by 10 from the moon. So notice that the null point is closer to the smaller mass. It is closer to the moon, away from the earth. I'm not at all talking here about center of mass. Center of mass is closer to the heavier mass, right? I'm talking here about null point, where a third mass should be placed so that it experiences no force. In the next hour, I will tell you that null point is the place where the net field is 0. Yeah, in the next hour, we are going to talk about fields. So without wasting time, let's see the next example. Now we will talk about the forces in the case of charges. So if we have got two charges q1 and q2 separated by distance r, we know that the force acting between them is given by k q1 q2 upon r square. Now this same force can be written in terms of Rather than K, we can write 1 by 4 pi epsilon naught Q1 Q2 upon R square. Now you will say, sir, why will anyone ruin this beautiful K and write an ugly 1 by 4 pi epsilon naught? This 4 pi comes y will make sense in Gauss law. Why this epsilon naught? Why are we talking in terms of a new quantity epsilon naught rather than our super beautiful K? It will make sense, just keep on listening. So rather than keeping our beautiful K, we like to make it ugly and write it as 1 by 4 pi epsilon naught because it has got its own advantages. Now, this quantity epsilon naught is nothing but permittivity of free space. When I say free space, it means vacuum. So for vacuum, here you have to substitute the value E naught. Now, if you place these two charges inside a medium, then what to write the equation as? I said that this value of K is 9 into 10 raised to the power of 9 for vacuum. For medium, we have to take up some other value. Which value? Here, we say that the force acting between the two charges is given by 1 by 4 pi epsilon naught Q1 Q2 by R square, where epsilon naught is the permittivity or free space, permittivity for vacuum. For a medium, in place of E naught, we write 1 by 4 pi epsilon m Q1 Q2 by R square. Here beta epsilon m is the permittivity of the medium. What is the relationship between permittivity of medium and permittivity of free space? We say that the permittivity of medium can be written as the relative permittivity into the permittivity of free space, or one can say that the relative permittivity is nothing but permittivity of the medium upon permittivity of vacuum. Do notice that relative permittivity is the ratio of permittivity of medium to the permittivity of free space. Relative permittivity is a dimensionless quantity. It has got no dimension, while permittivity of free space and permittivity of medium have the same dimension. So permittivity of free space has the same dimension as permittivity of medium, while the relative permittivity is a dimensionless quantity. It has got dimension of 1. The dimensionless quantities have got dimension of 1. So now question is, but sir, why somebody wants to use this ugly formula? Over the course of study, I will teach you something about dielectric constant. Dielectric constant. And for dielectric constant, I will use the symbol capital K. Yeah, same like Coulomb's constant, but it means something else entirely. So the symbol is K, but it is nowhere related to Coulomb's constant. We say that the dielectric constant is same as relative permittivity. So better understand, if the relative permittivity of a medium is 4, we also say that this means that the dielectric constant of the medium is 4. And if the dielectric constant of the medium is 4, relative permittivity is 4, it means that the permittivity of the medium is 4 times the permittivity of free space. The permittivity of medium equals to relative permittivity times permittivity of free space. If I am saying that the relative permittivity is 4, it means that the permittivity of medium is 4 times the permittivity of free space. If the permittivity of medium is 4 times the permittivity of free space, it means that the force inside this medium will be 1/4 the force for the same separation in free space. Because for same separation in free space, the force will be 1 by 4 pi epsilon naught Q1 Q2 upon R square. Then inside a medium of relative permittivity 4, you will get in the denominator an extra term of 4. So the force inside a medium of relative permittivity 4 will be 1/4. Similarly, inside a medium of relative permittivity 5, here you will write 5 times epsilon naught. So the force become 1 by 5 times. So if the medium has a relative permittivity ER inside the medium, the force for same separation of same charges comes out to be ER times smaller. So let's talk more about the Coulomb's law, but first we should know how to write Coulomb's law in vector form, just the way we learned how to write Newton's law of gravitation in vector form. So let's say we have got two charges Q1 and Q2. This vector represents the position of charge 2 with respect to charge 1. Now we know that the magnitude of force will be KQ1 Q2 upon magnitude of separation between them whole square. Magnitude of position vector of 2 with respect to 1 whole square. Now we know the magnitude of force, but here there is a catch. Catch is that the force will be attractive or repulsive depends upon the nature of the charges Q1 and Q2. If both will be like, the force will be repulsive. So if Q1, Q2 is greater than 0, the force applied by the charge 1 on charge 2 will be parallel to the vector R21. So parallel to R21. And if Q1, Q2 will be less than 0, then the force will be attractive. If both the charges are unlike, then the force will be attractive. And then the force will be anti-parallel to vector R21, or you will say the force will be parallel to vector minus times R21, right? So for the multiplication of charge greater than 0, the force is parallel to R21. For multiplication of charge less than 0, the force is anti-parallel to R21. Now see how beautiful the formula in this case comes out to be. You will say the force will have magnitude this. First of all, assume both of them to be positive. No worry. If both of them are positive, then the force will be repulsive and the force will be in same direction as that of vector R21. So you will write the direction of force is same as that of vector R21, and we have written a unit vector in direction of vector R21 written by R21 cap. So the force in vector form comes out to be the magnitude of force times a unit vector in the direction of vector R21. Now when you write this unit vector, you will write it as kq1 q2 upon R21 magnitude whole square into the unit vector of particle 2 with respect to particle 1 can be written as position of particle 2 with respect to particle 1 upon the magnitude of position of particle 2 with respect to particle 1. So here you get force equals to kq1 q2 into position of 2 with respect to 1 upon the magnitude of position of 2 with respect to 1 whole cube. Now bachcho, see here why I am saying this formula is beautiful, because here you just need to substitute q1 and q2 with sign. Observe that for q1 q2 greater than 0, both the charges are like, yes, the force will be repulsive, yes, so the force will be parallel to vector R21. So if q1 and q2 are like, q1 q2 will be greater than 0 and the force is parallel to R21. If q1 and q2 are unlike charges, then q1 q2 will be less than 0 and the force will be parallel to minus times of vector R21. So if q1 q2 will be less than 0, this quantity will be negative, so you will get a minus sign here, and then you can say that the force is anti-parallel to position of 2 with respect to 1. Yes, so substitute q1 and q2 with sign. Here this formula is self-adjusting in nature. If both the charges are like, you will get the right answer. If both the charges are unlike, even then you will get the right answer, because when q1 q2 will be less than 0, here you are automatically getting a minus sign, which tells you that the direction of force is opposite to the direction of position of 2 with respect to 1. So just remember that, substitute here q1 and q2 with sign. This is a beautiful formula. Here you do not have to worry about any minus. Just visualize both of them as positive while writing the formula and then substitute with sign. You will get the right answer. So moving on. If two charges are placed in vacuum at a distance r, apply a force F on each other. Determine the separation between the charges in a medium of relative permittivity ER to experience the same force. So there are two charges Q1 and Q2 separated by distance r in vacuum. Question is, how much has to be the separation between these two charges inside a medium of relative permittivity ER so that they experience the same force. So let's say inside the medium of relative permittivity ER, the separation between the charges is r dash. Now balancing out force, you will write F equals to k q1 q2 upon r square, or 1 by 4 pi epsilon naught q1 q2 upon r square, and this force has to be same as inside the medium. Inside the medium, we know that the force is written as 1 by 4 pi epsilon m q1 q2 by r dash square, and in place of epsilon m you can write epsilon naught epsilon r. So you can write here 1 by 4 pi epsilon naught epsilon r q1 q2 upon r dash whole square. They are asking you in question, force in both the cases have to be same, then what has to be the new separation? So now it's a simple question. Cancel out bacho, 1 by 4 pi epsilon naught, 4 pi epsilon naught, q1 q2 q1 q2. So from here you get 1 by r square equals to 1 upon er into r dash whole square. So on solving, you get r square equals to er into r dash square. Taking under root both the side, you get r dash equals to r by root er. That is r upon under root of the relative permittivity of the medium. So here, taking under root both the side, you will get r equals to root er into r dash. So r dash comes out to be r upon root er. Simple. Let's move on. Determine the force on one charge due to other two for three equal charges q placed at the three corners of an equilateral triangle of side length a. So now the same type of question as we have done in gravitation. Now rather than having three masses, they have given me three charges. But there is a catch. Masses always attract each other. Gravitational force is always attractive in nature. But electrostatic force will be attractive or repulsive. That depends upon the nature of charges. Here we can see all the three charges are like in nature. Then how to write the force? Now visualize the force on any one of the charge A due to the other two charges. So because of B, as B and A have got charge of similar type, B will repel A. And this force will be equals to K into Q upon separation between them whole square. So that will be KQ square upon A square. Because of C also, since A and C have the same sign of charge, C will also repel A. So there will be one more force, that will be K into Q upon A square, KQ square upon A square. And the angle between these two forces applied by B and C will be nothing but 60 degree, as this angle is 60 degree. Now you know what are the forces acting on A, their magnitude, and what is the angle between these two forces. You can find the resultant force. You will say that the resultant force equals to 2F cos theta by 2. If you have got two forces F and F acting at angle theta, then the resultant comes out to be exactly midway, equals to 2F cos theta by 2. Use the same thing here. So you get 2 into F KQ square upon A square into cos 60 by 2. Cos 60 by 2 is cos 30. Cos 30 is root 3 by 2. So you get 2 into KQ square upon A square into root 3 by 2. Cancel out 2 and 2. So the force comes out to be root 3 KQ square upon A square. The same type of force we got in gravitation, but there is a catch. Here, the forces are repulsive in nature. So all the charges will try to move away from each other. In case of gravitation, when you place equal masses m, they were attracting each other. So the force on any one of the mass was towards the center. Here they are repelling, as they are charges of same nature. So sir, can here a question just like gravitation can be formed? Yes, but in a different way. See how. Question is, now you have got three identical charge q placed at the three corners of an equilateral triangle. Question is, where should a fourth charge be placed and how much magnitude so that the system is in equilibrium? So where should a fourth charge be placed and how much magnitude so that the system is in equilibrium? From the first part I have solved, I already know that the force on this charge is root 3 kq square upon a square away from the center. This one root 3 kq square upon a square away from the center. This one root 3 kq square upon a square away from the center. They have got charge of same type. They will try to run away from each other. Where should a fourth charge be placed so that the entire system is in equilibrium, and what has to be the magnitude of that fourth charge? So you'd say, sir, because of symmetry, you should place the fourth charge at the point of symmetry, which is the centroid. Now, simple question. What has to be the nature of this charge? If these three charges are positive, should I even place the fourth charge as positive? No, sir. Why? If you place the fourth charge as positive, it will also repel A, and then A won't be coming back. It will also repel B, then B won't be coming back. So this is obvious that the fourth charge should be placed at center, and that charge should be negative in nature. So if A and C are repelling B, then this fourth charge will attract B, and the net force on B can be 0. So I have solved already much part of this question. The fourth charge should be placed at the centroid of triangle, and the fourth charge should have the opposite nature, that of these three charges. So if these three charges are positive, the fourth charge should be negative, and if these three charges are negative, then the fourth charge has to be positive. So the fourth charge should be placed at the center of triangle, centroid of triangle, so that the net force on fourth charge is 0. The fourth charge should be of opposite nature. If these three are positive, then the fourth charge should be negative. If these three are negative, then the fourth charge should be positive. So let's say we have placed this fourth charge. Now see, for positive charge we are using blue color, and for negative charge we are using red color. First of all, can you tell me what will be the separation of this fourth charge from one of the charge? The same thing. What same thing? So if you think of this distance as r, and you drop here a perpendicular, okay, this half length will be a by 2, yeah, and this half angle will be 30 degree because the complete angle you know is 60 degree, so half angle will be 30 degree. Now if you look into this right angle triangle, you will say that cos 30 r cos 30 equals to a by 2. Okay, right. So using the same thing, we can say the net force acting on one of the charge due to other two, root 3 kq square upon a square, has to be equals to kq, and take the central charge as capital Q upon r square. What is r? The separation between central charge and this charge. Now we can write the separation between central charge and this charge in terms of A as r cos 30 equals to a by 2, the same thing. So r root 3 by 2 equals to a by 2, cancel out 2, you get r equals to a by root 3. Same as we did for gravitation. Now substituting here r, you will get root 3 kq square upon a square equals to kqq upon a by root 3 whole square. Now here we have got a by root 3 whole square. So in the denominator of denominator, after squaring, this becomes a 3, and here you get a square. So the k get cancelled, a square get cancelled. This root 3 after squaring moves from denominator of denominator to numerator, and you get a 3. So k get cancelled, q one term get cancelled, a square get cancelled. What you get is q equals to root 3 q, or capital Q comes out to be equals to q by root 3. Now notice here I have placed here a minus sign. Why minus sign? It's a minus sign because this charge at the center need to be of opposite nature of the other three charges. So that's why the charge at the center has to be 1 by root 3 times the charges placed at the three vertices and should have the opposite nature. That's why a minus sign. So moving on. Question is, now we have got four charges A, B, C, D placed at the four corners of a square. Question is, find the force on charge A due to the other charges. Now charges can be positive as well as negative in nature. Now tell me, the charge B will attract A or repel A. So the charge B will attract A. The charge C will repel A or attract A. So the charge C will repel A because A and C have got same nature of charge, both positive. The charge D will attract A. So first of all, visualize the forces on charge A due to each individual charge. Because of B, there will be a force of attraction. How much? KQQ, magnitude of charges, upon separation between them, A whole square. Similarly, because of D, there will be a force of attraction. How much? KQ square upon A square. And because of C, there will be a force of repulsion. But notice that here the separation shouldn't be taken as A. The separation should be taken as the length of the diagonal. That will be root 2A. So you get KQ square upon root 2A whole square. Now, once you have visualized the forces on charge A due to the other three charges, game over. You can say that the resultant of these two, KQ square upon A square and KQ square upon A square, will be nothing but root 2 KQ square upon A square in direction opposite to the force by the C, which is repulsive. And this KQ square upon root 2A square can be written as KQ square upon 2A square. So visualize the forces. So because of C, the force will be KQ square upon 2A square repulsive, and because of these two, KQ square upon A square, KQ square upon A square acting at angle of 90 degree, you will get root 2 KQ square upon A square. So the net force acting on the charge A will be root 2 KQ square upon A square minus KQ square upon 2A square. Obviously, this force is more. This is root 2 times KQ square upon A square. This is half of KQ square upon A square. So the net force on A will be towards the center. And this net force on A will be equals to root 2 KQ square upon A square minus KQ square upon 2A square. You can take KQ square upon A square common and write root 2 minus 1 by 2. So sir, what is the key to write force on any one of the charge? Write the force on the charge due to all the other charges, and as force is a vector quantity, do the vector sum. That's the key. Now let's talk about null point in the case of charges. So for like charges, if both the charges are positive or if both the charges are negative, then you get the case exactly same as that of gravitation. So remember that if both the charges are positive or if both the charges are negative, then it's the same case as of gravitation. In case of gravitation, if we have got two masses m1 and m2 separated by some distance d, where do you find the null point? On the line joining the charges in between the charges. At what distance from m1? At a distance of root m1d by root m1 plus root m2 from m1, and at a distance root m2d by root m1 plus root m2 from m2. This is the position of null point. So similarly, if you have got like charges q1 and q2, the null point is found on the line joining the charges in between the charges, somewhere between q1 and q2. And the null point is between the charges closer to the charge of smaller magnitude. So if q1 has got magnitude less than q2, then you will say that the null point will be closer to q1, and if q2 has got magnitude less than q1, then you will say that the null point will be closer to q2. So the null point for like charges is found on the line joining the charges in between the charges closer to the charge of smaller magnitude. Now, if the null point is found at distance x from q1 and d minus x from q2, you can do the same mathematics. You can say if I place a charge q dash here, the force because of q1 should be same as the force because of q2. So k q1 q dash upon x square equals to k q2 q dash upon d minus x whole square. And on solving, you get x equals to root q1 d upon root q1 plus root q2. Same as we got for gravitation. So if we visualize the two charges q1 and q2, and we think of the null point, then the distance of null point from q1 is root q1d by root q1 plus root q2, and the distance of null point from q2 is root q2d upon root q1 plus root q2. This is the case same as that of gravitation when both the charges are like. Remember that. Do you have got positive and negative mass? No. You have got only one type of mass? Yes. So if you have got only one type of charge, that case is same as that of gravitation. If you have got only one type of charge, that case is same as that of gravitation. Beta, one more thing here. Substitute q1 and q2, only the magnitude, not the sign. Hai na? Somebody might substitute here a negative charge q2 and then say, sir, if you are substituting here a negative charge q2, then you are getting a complex number. Don't do that. Just substitute here the magnitude of q1 and q2. So let's move on to the second case, which now we need to focus if the charges are unlike. Now let's say we have got these two charges q1 and q2 separated by distance d, and they are unlike charges. So if one of them is positive, another one is negative. And let's say we are thinking of the case where the magnitude of q1 is greater than the magnitude of q2. So magnitude wise, q1 is more than q2. So the charges can look like minus 4 coulomb, 2 coulomb, or the charges can look like 6 coulomb, minus 3 coulomb. So the magnitude of q1 is greater than q2, and they have got opposite nature. One of them is positive, another one is negative. So now where do we find the null point? In this case, the null point is found on the line joining the charges, outside the charges, and closer to the charge of smaller magnitude. So let's say if I have got charge of minus 9 coulomb and 4 coulomb, where do I find the null point? The null point is found on the line joining the charges. I have drawn that line. Outside the charges. Okay, so not in the region between them. Okay. Closer to the charge of smaller magnitude. So somewhere here. One more example. If we have got, let's say, charge of 8 coulomb and minus 6 coulomb, where do I find the null point? On the line joining the charges. I have already drawn that line. Between the charges? No. Outside the charges. Closer to the charge of smaller magnitude. So somewhere here, closer to the charge of smaller magnitude, you will find the null point. If I give you minus 12 coulomb and 18 coulomb, where do you find the null point? On the line joining the charges, outside the charges, closer to the charge of smaller magnitude. Somewhere here you will find the null point, not in this region. Okay. So let's say we have got these two charges q1 and q2. We know that we find the null point outside the charges, closer to the charge of smaller magnitude, and in this case I am taking q2 to have smaller magnitude than q1. That's why I have taken the null point here. Now you will write from force balance k q1 q dash upon d plus x whole square equals to k q2 q dash upon x square, cancelling out k q dash and taking under root, you will get root q1 upon d plus x equals to root q2 upon x. The distance of the null point from the charge q2 will be given by root q1d upon root q1 minus root q2. So visualize the two charges in space. Remember that the null point will be formed on the line joining the charges, outside the charges, closer to the charge of smaller magnitude somewhere here. Here I have told you that the magnitude of Q2 is less than the magnitude of Q1. Now this distance comes out to be equals to root Q2d upon root Q1 minus root Q2. And the distance from Q1 comes out to be root Q1d upon root Q1 minus root Q2. So how to remember? See better. For like charges, we got the null point at how much distance from Q1? So we got at root Q1d upon root Q1 plus root Q2. So for like charges, you got in denominator plus. For unlike charges, in denominator you just get a minus. So the distance from Q1 comes out to be root Q1d upon root Q1 minus root Q2. And it's obvious, if Q2 has got less magnitude than Q1, then root Q2 should be subtracted from root Q1. In case of addition, you have got no problem, root Q1 plus root Q2 or root Q2 plus root Q1, when you have got like charges. But when you have got unlike charges, you are subtracting. So you should have this in mind, which one is subtracted from which one. Isn't it obvious that larger one minus a smaller one? So root q1 minus root q2. So the distance from q1 comes out to be root q1d upon root q1 minus root q2, and the distance from q2 comes out to be root q2d upon root q1 minus root q2. So now let's practice some questions based on this. The first question: if you have got two charges of minus q and plus 9q, where should a third charge be placed so that it does not experience any force? They are simply asking you the position of null point. So where should I place the third charge so that the net force on third charge becomes 0? So we have learned that since these two charges are unlike in nature, where we should place the third charge? On the line joining the charges, outside the charges, closer to the charge of smaller magnitude. So on the line joining the charges, outside the charges, closer to the charge of smaller magnitude somewhere here. So visualize that we have placed the third charge somewhere here, and this third charge is q dash. Now, if the net force on this third charge has to be 0, then the force because of these two charges have to be equal and opposite. So the magnitude of force due to these two charges should be same. The magnitude of force due to these two charges should be same. So you can write kq dash upon q upon x square. I am just writing the magnitude equals to kq dash into 9q upon d plus x whole square. Now we can cancel out k, q dash, q and q. And taking under root both the side, I can write on the left hand side 1 by x equals to 3 upon d plus x. Now you can write d plus x equals to 3x, or d equals to 2x, or x comes out to be equals to d by 2. Sir, can I do the same question using the formula you have just taught? Yes. The distance from q will be equals to root q into d upon greater one, root of 9q minus root of q. Now this quantity root q into d upon root of 9q minus root of q, here from each term you can take root q common. So you get root q into d upon root q times root 9 minus 1. And with a root 9 minus 1 becomes 3 minus 1 2, and this root q get cancelled, so you get d by 2. So sir, can I simply mug up the formula and use it? Yes, you can use the formula, but remember that whenever you are substituting root q1, root q2, do not substitute with the sign, okay? Because root of negative is a complex number, that doesn't make sense. So one last example before we finish off this hour. So the example goes like, there are two charges q and 4q. Where should a third charge be placed of how much magnitude so that all the three charges are in equilibrium? So question is, where should you place a third charge and how much has to be the magnitude of third charge so that all the three charges are in equilibrium? So first of all, sir, since the two charges are like, I know that the third charge should be placed on the line joining them, in between them, closer to the charge of smaller magnitude somewhere here. Then only the third charge will experience zero force. The force because of charge q and 4q will cancel out. So let's say the third charge has to be placed between the two charges, closer to charge of smaller magnitude, right? And let's say we have placed the third charge at distance x from the charge first one, which is q. So you will say k into q dash upon this distance x whole square equals to k into q dash into 4q, the second charge q2 upon d minus x whole square. Sir, why are you not directly using the formula? You can use the formula directly as well, that the distance from q1 will be given by root q1 into d upon root q1 plus root q2. Okay, but I am trying to go through the basics. So cancelling out beta k, q dash, q and q, and taking under root both the sides, we will write 1 by x equals to 2 upon d minus x. Now cross multiply, you will get d minus x equals to 2x, or you will get d equals to 3x, or x comes out to be equals to d by 3. So the distance from the first charge of q has to be d by 3, and the distance from 4q comes out to be 2d by 3. So you should place a charge at distance d by 3 so that the charge experiences no force. But there is one more catch in the question. Question is, and how much magnitude so that all the three are in equilibrium? If you place one more charge here at distance d by 3, no matter how much charge you are placing at distance d by 3, it will experience no force. But they are saying how much charge should be placed here so that even these two are in equilibrium. So sir, what to do? See better. Let's assume that q is positive, 4q is positive. Can I place the third charge at distance d by 3 also positive? No, sir. If you place the third charge also positive, na sir, then this q will be repelled by 4q as well as by this third charge, let's say q dash, and hence it can't be in equilibrium. So what to do? Sir, the third charge you are placing at distance d by 3 from q should have opposite nature. So this q dash should have opposite nature to that of q and 4q. So if 4q repels this q dash attracts it. And then only the net force on this q can be 0. So assuming the charge placed to be q dash, now you can say the force because of this q dash on this q1 should be same as the magnitude of force because of this q2 on this q1. So you will say kq dash into q, the charge q, upon d by 3, the distance d by 3 whole square, equals to k into q into 4q, the force because of 4q on q, upon the distance between them d square. So cancelling out k, q, you will write q dash upon d square by 3 square, and 3 square becomes 9, it goes to numerator, equals to 4q by d square. Now cancelling out d square, you get 9q dash equals to 4q, or q dash should be equal to 4q by 9. But this won't be the appropriate way to answer it. Why? Because the third charge to be placed should have opposite nature to this q and 4q so that it attracts. So the proper answer will be that, but the charge has to be opposite, so we say that q dash has to be equals to minus 4q by 9. So the force, the third charge placed here should be of opposite nature compared to this q and 4q. So that's all in this hour, and in next hour we will start talking about field. See you guys in next hour. Bye bye.